All right. So on Thursday, we looked at a few or two of the other options. We looked at the integral test, and then we looked at the comparison tests for determining if a series was convergent or divergent. And we also have the test for divergence that we looked at in section 11.2 as another option to determine if a series is convergent or divergent as well. Tonight, we're going to look at alternating series as another test for it. And then we're also going to look at the absolute convergence, which would be the root test and the ratio test for convergence and divergence. So an alternating series is a series that goes from positive to negative values. So it goes back and forth. So they're always going to have that -1 to the n power in there. So if it's -1 to the n minus 1 power, it's going to start off as a +1. If it's just to the n power, it'll start off as a -1. So, and they're going to alternate back and forth. So this is an alternating series. For example, cosine does switch back and forth between positive and negative, but since it doesn't do it at every other value, it is not alternating. So alternating has to go positive, negative, or negative, positive. It has to constantly switch back and forth. So we'll see it in those two different ways there. When we're looking at it, the Bn is actually a very important piece. So that's basically the series part of it, and then the alternating part is that -1. So we want to be able to separate out those two, because when we're looking at doing the test, we're going to look at that, the actual series piece without the alternating part in there as well. So the alternating series test, as long as it alternates, it has to satisfy two criteria. As long as it satisfies both criteria, then the series is convergent. The first criteria is that it's decreasing, so that the b to the n plus 1 is always less than or equal to b to the n, or b sub n. So this way, the series is always decreasing if you eliminate the negative sign. The second part is that the limit of the series without the negatives has to equal 0. So if you eliminate the alternating piece, the limit has to equal 0. As long as it meets those two criteria, then the series is convergent. So we're going to look at the alternating series test whenever you have that -1 in there. It's a quick one to look at because we really don't have to test that much stuff. And it's a little easier than trying to do like the integral rule and stuff like that on it. All right, so let's look at what's known as the alternating harmonic series, because we already knew that the harmonic series that we tested before is not convergent. So if there was no sign changes, it's not convergent. But let's look at the alternating harmonic series. So the alternating harmonic series goes 1, -1, 1/3, 1/4, but signs are changing. So it's -1/2, +1/3, -1/4, +1/5, and so on and so forth. If we look at the two criteria for the alternating series test, the first one is each term, does it keep decreasing? And that it does. 1 over n plus 1 is less than 1 over n. So it meets the first criteria. Then the second criteria is, does the limit as n goes to infinity equal 0? So 1 over n, as n goes to infinity, it does equal 0. So the alternating harmonic series actually does converge because of the alternating series test. So the harmonic series does not, but the alternating harmonic series does. Does everybody understand how we use those two criteria to test it? Let's do a couple of them. All right, so here's my first problem. So we've got the series -1 to the n 3n over 4n minus 1 is alternating. So now we got to figure out, does it fit the two criteria? The first criteria is that the series is decreasing. So if I look at this series quickly, can we tell if this one's decreasing really quickly or no?
It's not.
All right, so is it not decreasing, or can we not tell?
It's not decreasing.
Okay. How do you know that it's not decreasing?
If we do as n approaches infinity on the bottom, and it's also doing the same thing essentially on the top. And it'll always be higher on the top because, well, it'll be 3 over 4 pretty much.
Right. So the bottom's actually bigger than the top. So
Yeah.
that's the thing when we're looking at it. So you're looking at two different things. You're looking at the limit as it's going to infinity, which is that's the second criteria. The first criteria is it decreasing? So is the second term smaller than the first term? And so on and so forth. So when we had 1 over n, it was really easy to see that because there was just nothing on the top. So it was quick. And this one, when we have n on the top and the bottom, it's a little harder to determine that. However, there's two criteria. They have to meet them both. Which you just showed, actually, is that it doesn't meet the second criteria. So if you look at the second criteria, that's where the limit, as n goes to infinity, has to equal 0. And what you just showed by doing the infinity, basically on the top and the bottom, and let's try this again, is that the limit as n goes to infinity really goes to 3 over 4. And it's not 0. So since my limit does not go to 0, it fails the second criteria. So the thing about the alternating series test is it tells us if it's convergent, but it does not tell me if it's divergent. So since it doesn't tell me that it's divergent, I have to use a different test to be able to show that it's divergent. I just know it fails the alternating series test right now. Does everybody understand that?
Yes.
Okay. So it's kind of one of those things like you automatically, like, I don't want you to make the assumption that it's like, okay, if it fails this, it has to be the other one. That's not the case. It can fail a test and we actually know nothing about it. This test only tells us the positive side. If it passes it, it's convergent. Other than that, we don't know. So we have to use a separate test to be able to show if it's convergent or divergent at this point. So on this one, what we can look at is if we look at the test for divergence, the test for divergence says if we look at the limit of the regular function, if that limit doesn't exist, it diverges. So the test for divergence says if the limit doesn't exist, then it diverges. So if we look at this one, since this limit of -1 to the end, it's going to bounce back and forth above and below. Since it doesn't actually come to a specific value, therefore the test for divergence says since the limit doesn't exist, it diverges, and that's what this one does.
So if it doesn't make those two those two criteria, it automatically diverges. Like either one of them, if either one of them it doesn't work, then it diverges.
No. If it doesn't meet one of those two criteria, I have to do another test to show what it does. So even if it doesn't meet those two criteria, it could still converge. We just have to use a different test to show that it converges or diverges. So the alternating series test doesn't give me any information if it fails. Just like the test for divergence, if it passes the test for divergence, I know it diverges. If it fails the test for divergence, I don't know if it converges. I just know it doesn't pass that test. Does that make sense? right, let's look at another one. We'll see if I can make it a little more sense. Because one of the big parts of the test is most of the questions on the test, you're literally going to tell me if it converges or diverges. That's the main part of the test. All right, so let's look at this one. So first off, is this an alternating series? That's the first thing we have to decide if we're going to use an alternating series test.
Yes, it's an alternating.
Yes, this is an alternating series test. Because it's got, or it's alternating series because it's got the -1 in front. All right, second part. Does it, so we have to do two tests. We have to figure out, does it decrease in value? And is the limit going to 0? Now, you can do either one of those tests at any point. So like you don't have to do condition 1 first and then do condition 2. So you can look at it and say which one's easier to test first. And if it works, then test the other one. If it doesn't work, then you're done because it has to meet both criteria. So if we look at this one, it's probably pretty quick to see if the limit goes to 0. Because I really just have n squared over n to the third plus 1. So what am I going to divide all those by to find the limit?
N to the third.
Right. So if I divide it by n to the third, I'm going to get on the top 1 over n, and then on the bottom I have 1 plus 1 over n to the third. So 1 over n, as the n goes to infinity, that top is going to what?
0.
Right. So that means the whole thing is going to 0. So it meets criteria 2, or it meets condition 2, that the limit goes to 0. So since we could do that one quick, now let's look at the first one. It's got to be decreasing. So we've got our function there. The problem is, just like the last one, to tell if it's decreasing is kind of difficult to do because I have stuff on the top and the bottom. So one of the easiest ways to figure out if something's decreasing is we look at the derivative of it. So how do I find the derivative of n squared over n to the third plus 1?
Can you use L'Hopital's rule?
L'Hopital's rule will help you find the limit, but it won't help you find the derivative. Because L'Hopital's rule basically is saying you do the derivative of the top, derivative of the bottom, and then you can look at the limit of that one. That helps you get rid of those things. So that would have helped us in criteria 2, but not in criteria 1. So to find the limit or find the derivative of this, we're actually having to do the quotient rules. So you take the derivative of the top. What is it? Derivative, wait. It's the derivative of the top times the bottom, and it's plus the derivative of the bottom times the top. And then divided by the bottom squared. So the derivative of the top is x, or 2x, and the derivative of the bottom is 3x squared. So we break all that down and do it all out, we end up getting, that's the derivative. So the question is when is that less than 0? So the bottom, can the bottom ever be less than 0? Because when we're looking for less than 0, basically I'm looking for negatives. So can the bottom of that fraction ever be negative?
No.
No, because it's squared. So really, I only have to look at the top. So as long as the top is less than 0, then the whole thing is less than 0. So if we look at just the top, 2 minus x to the third has to be less than 0. So that means x has to be greater than this cubed root of 2. So I know that it's not always decreasing, but as long as it decreases, it continues to decrease over time after a certain point, then we consider it decreasing. It's the same thing we were doing last week. We looked at the one with the e. We said after e, it decreases. Same concept here. After the cubed root of 2, it's decreasing. So we can say this function decreases. So we know it decreases, we know the limit's 0, and we know it's an alternating series. So as long as it met all those criteria, it converges. Does that make sense? Would you like another one?
Yes.
Okay. Let's do one more. Let me actually give you guys one to do. Let's do that one. All right, try that one. Remember, you're looking for those 3 criteria. Is it an alternating series? Which I'll tell you it is, because otherwise I wouldn't have put it up there. And then, so does it decrease? And is the limit 0? All right, which one of the 2 criteria or conditions do you want to try first on this one? Do you want to show that the limit equals 0, or do you want to show that it decreases first?
I started with the limit.
Yeah, the limit's normally the easiest one to start with, and if it doesn't work, you're done. Unless you can quickly look at it and say, oh, yes, this is decreasing. So if you started with the limit on this one, does the limit equal 0?
Yes.
Yeah, I'm actually going to paste you what they did in the book. I don't like what they did in the book, but I'm going to show it to you anyway. Because they, to know how the rules, they always divide by the highest exponent. They divided them by the square root of n, and I'm not sure why. I would have divided them all by n, and then you get 0 on the top over 3. Oh, no, sorry, 0 over 2. So it still comes out to be 0. All right, so my limit equals 0. So we know that part. So the only next piece that we have to do is we have to do the less than the derivative basically to figure out if it's less than 0. Smaller. So the beginning of the derivative so that's if you have the so it's the derivative of the top times the bottom of the bottom times the top over the bottom squared. And then we can simplify that down to that. So again, in the bottom here, the bottom can never be negative. Because the x is always going to be positive. The bottom part's going to be positive, and you can never have a negative square root. So the bottom can never be negative. So you're just looking at the top. So x has to be greater than 3 over 2 for it to be decreasing. So as long as n is greater than 2 or equal to 2, then it decreases. So it decreases, its limit is 0, and it's an alternating series. So that means what?
It's convergent.
It is convergent. Yeah, let's do one more of these. All right, so let's try this one. All right, so this one is it alternating?
Yes.
All right. If we did is this one decreasing? So e to the 2 divided by n, does that decrease as we go up?
I mean, it goes to 1. It would go to 1, right? Two
Yeah.
divided.
Yeah, so you're going to divide it. So eventually it'll go to 1. But is each value, so is the the second value going to be smaller than the first, and so on and so forth? Does the function decrease over time? So it's going to 1, but is it increasing going to 1 or is it decreasing going to 1?
I think it would increase.
I think it decreases maybe.
Yeah, this one's decreasing. So as n's getting bigger, that fraction's getting smaller. So therefore, the beginning one, so e to the second would be the first one, because that'd be n is 1. And then e to the first would be the second one. So it's going to get smaller. It's going. So it is decreasing. However, you did point out one very, very important piece. The limit as n goes to infinity doesn't go to 0. It goes to 1. So it fails criteria 2. So it fails the alternating series test. Now, since it fails the alternating series test, I have to check something else. If it fails the alternating series test, always do the test for divergence next. Because 99.9% of the time, it will pass the test for divergence. Because if you have an alternating series, it's bouncing between positive and negative values. And the limit, you can't actually go to a specific limit if it's bouncing between positive and negative values. So because it's going to 1 at the end, it's not going to 0. So it's going to go to positive 1 and negative 1, and that's not going to help us.
Yeah, isn't it just going to alternate between positive and negative 1? It's not going,
It's not going to go to 1 value.
but how can we say that it's decreasing then? Because it's just like dancing between 1 and negative 1.
Right. So, but the decreasing value, so when you're looking for decreasing, and even when you're looking at the limit, you're not looking at the alternating part. You're just looking at the Bn part. So in this case, all we're looking at is that E2 divided by n.
Okay.
So the alternating series test ignores the alternating part because that's the first criteria. It has to be alternating. So we ignore that piece altogether. And we're just looking at the series, not the actual negative 1, to determine the 2 criteria, that it's decreasing and that it goes to 0. Does that make sense? So that's why if you look back at, let's look at this one real quick. See how in this one, I was doing the limit of n2 over n to the 3 plus 1. I didn't even look at that first part. But since it goes to 0, I'm able to, it passes that criteria. And the same thing with this one. I just looked at the square root of n over 2n plus 3. I didn't look at the beginning part. So when you're doing the alternating series test, you don't look at the alternating part because we assume that piece before we look at the 2 conditions. But when we're looking at, if it fails the alternating series test, when we're looking at anything else, we do have to keep that in mind. And that's why almost always it fails the test for divergence, because it does bounce back and forth. So this one's going to diverge because of the test for divergence, not because it failed the alternating series test. All right. Let's look at a couple more tests. All right, so we have absolute convergence, and then we have the ratio and the root test. Absolute convergence means that it's going to converge. Basically, the absolute values are going to converge. So that means if it's always negative, if it's always positive, if it alternates, it doesn't matter. It's going to always converge. That's what absolute convergence is. So if we can prove that it absolutely converges, I know all those options are going to converge. So I know the alternating series would converge, I know the negative series is going to converge, and I know the positive series is going to converge. Not all functions are absolutely convergent. And we've seen one already. The harmonic series is not convergent, yet the alternating harmonic series is. So that's one of those ones that we can look at and go, it's not always convergent. So all we have to do to show that a series is absolutely convergent is if we take the absolute value of that function and it's convergent, then the whole series, then it's going to be absolutely convergent. So we have this series. It's an alternating series, the -1 n minus 1 over n squared. And we can look at this for the alternating series test if we wanted to. But if I take the absolute value of it, I know that 1 over n squared is going to converge because it's a p-series. So remember those back from when we first started the p-series and the geometric series? So since this is a p-series and p is 2, it converges. And since I did it with the absolute value, therefore that whole function, that series is absolutely convergent. So its positive version, alternating version, and negative version will all converge. Now the harmonic series I just talked about. So the alternating harmonic series I know is convergent. However, if I took the absolute value of it, I have the harmonic series. Now the harmonic series is not convergent. So this is an example of one that's called conditionally convergent. It's only convergent when it's in the alternating state, not when it's in the positive or negative state. The alternating series or the absolute value series also helps us with cases that are not necessarily alternating. So if we have a series such as this one, cosine of n over n squared. So cosine of n is not always, it doesn't go positive, negative. So this is not an alternating situation, but it does have positive values and it does have negative values. So since I couldn't use the alternating series test at all on this one, we can look at it in terms of the absolute convergence though. If I did the absolute value of both sides of that, I'm doing the absolute value of cosine of n over n squared, because n squared is always going to be positive. I don't have to worry about the absolute value of that one. Now, I do know that the cosine of n is always going to be less than 1, because cosine goes between -1 and +1. So the absolute value of it's always going to go between 0 and 1. So I know that cosine of n over n squared is less than 1 over n squared, always, or equal to. 1 over n squared we know is convergent. That's the p-series. And since I know 1 over n squared is convergent, and cosine of n over n squared is less than it, then I know it's convergent because of the comparison test that we looked at last week. And since it's convergent there, it's absolutely convergent. So the original function cosine of n over n squared is also convergent. Does that make sense?
Yeah.
So we have to do multiple convergence tests to verify that it's absolutely convergent, essentially.
Well, you're not actually doing multiple convergence tests. You're really only doing one. You're doing the test on the absolute value of it.
Oh.
So like this one, so the absolute convergence isn't actually a test to tell me if it's convergent or not. Absolute convergence states that if I take the absolute value of it and that function is convergent, then all those options are also convergent.
Okay.
So in this case, I tested the absolute value or the absolute one, found out it was convergent by the comparison test. So that's actually the test I did. And since we did the absolute value originally, the original function is convergent. That's the thing, as we go, it's like we're adding more tests. Sometimes you're actually going to do multiple tests because one test you're going to do just isn't going to come up with the information you need. And we have to try something else. So it is unfortunately the one thing that makes chapter 11 a little more complicated. Thursday's class, we're actually going to do section 11.7, which is all the tests. And all we're going to do is look at problems and determine, and we have to figure out what test we're going to use and then determine if it's convergent or divergent from that test. So it's kind of like a review of all the different sections we've done already. All right, there's two other tests that fit along with the absolute convergence. The first one is the ratio test, and the second one is the root test. The ratio test states if I take the a n plus 1 over a to the n, or a sub n, if I do the limit of that and it's less than 1, it's absolutely convergent. If it's greater than 1, it's divergent. So this is one of those tests that actually tells me if it's convergent or if it's divergent in the actual test. And if it equals 1, we don't know and we have to try something else. So if the limit's less than 1, it's convergent. If it's greater than 1, it's divergent. And if it's equal to 1, we don't know and we have to try something else. The nice thing is the root test that we're going to look at is the exact same set of rules if it's less than 1, greater than 1, or equal to 1. So you don't really have to remember, as long as you remember that less than 1 is convergent, greater than 1 is divergent, and equal to 1 is nothing. You're pretty good with these two rules. All right, let's do a couple. All right, so if we look at this one, we can look at the 1 over n squared. So if we look at 1 over n squared, which we know converges because this is a p-series test. So if we do, we're basically doing 1 over n plus 1 squared over 1 over n squared, because that's the a sub n plus 1 and a sub n, which is n squared over n plus 1 squared. And if we divided them all by n squared, we get 1 over 1, which is 1. So the limit, so the ratio test for 1 over n squared, the limit goes to 1. I know it's convergent, so, but the ratio test doesn't give me that information. Do you see how it's that one, how it works? And how we got the limit of 1?
Yeah, I get that.
All right. Now, if I look at the harmonic series, 1 over n, I know that one's divergent. If we do the same thing, the 1 over n plus 1, 1 over n, that one also goes to 1. So that's why that if it equals 1 doesn't really help, because some of those functions are going to go to 1 and be divergent. Some of those functions are going to go to 1 and it's convergent. So that's why that value doesn't give me any information. And we have to use a different test. No, actually, I want to do this one first. All right. So we want to test this series for absolute convergence. So if you look at this one, we might say, okay, well, it's an alternating series. So let's do the alternating series test. The problem is that we've got n to the third and 3 to the nth power. So it's kind of hard to determine the information from this one. So whenever we have the n like that, look at the ratio test. It typically comes out a little bit easier. So let's look at the ratio test for this one, which when I show you, you might not think it looks easier. Actually, can I make that bigger? I can. All right. All right, so this is what the ratio test looks like. So I have n plus 1. I'm replacing all the n's with n plus 1, and then I'm just putting it. And notice I'm keeping the negative 1 there because we don't change in this one. We're not eliminating the negative 1 in this one. However, once I take the absolute value, my negative 1s are going to disappear anyway. So I end up getting the n plus 1 to the third over 3n plus 1 and n to the third over 3 to the n. So, oh, that should actually be a 3, not an n. So n plus 1, it's weird. Yeah, that should be a 3 there. So n plus 1 to the third power and 3n plus 1, and then 3 to the n. So they just take the bottom fraction and flip it over. If we look at this, 3 to the n plus 1 is no different than saying 3 to the n times 3. Because remember, addition is just the multiplication of like bases. So I have a 3 to the n on the bottom, and I have a 3 to the n on the top, so I can cancel those 3 to the n's out. And that's where that 1/3 comes from there. Because it's that the 3 to the first power that's left over. And that's where that 1/3 is. Then I have n plus 1 to the third power and n to the third power. So that's where I get the n plus 1 over n to the third power. Does everybody understand how I made it to this point? Except for the fact that that should be a 3. Everybody good to this step down here?
So
Good so far.
Good.
the 3 in the second, like the second one where it gets kind of crazy after the an plus 1 over an, the second one, those 2 3s cancel out from the n plus 1 cubed and the n cubed. Both of those cancel out, so where they go away.
Yeah, so basically this part right here. So let me actually type it in. So this 3, that becomes 3 to the n times 3 to the first, or just 3. That's what that 3 to the n plus 1, that becomes that. So that's how that 3n down the bottom there and the 3n up top cancels itself out. And the only thing that really changed from this first part here with the absolute value to the second part is the negative 1s disappeared because the absolute value gets rid of the negative 1s. And then it was just the keep, change, flip. From you kept the top fraction, you changed the sign to multiplication or division to multiplication, and you flipped the second fraction. That part, does that make sense now, or you still a little off on that one? Okay. So when we get down to the 1/3 n plus 1 over n, I can then divide that. So that's how I get the 1 plus 1 over n to the third power. Now, as n goes to infinity, because that's in essence what I'm doing, this part goes to 1. So I end up having 1/3 is my limit. And since my limit is less than 1, therefore my function, it passes the alternating, or not passes, it passes the root or the ratio test. So it passes the ratio test because it's less than 1, and therefore it is absolutely convergent. All right, let's look at another one of these. So this one, I have n to the nth power over n factorial. Does everybody remember what factorials are?
Yeah, can you divide factorials? Like if there's one on top and bottom, can you
You can-
divide them out?
You can cancel out like terms, but you can't necessarily divide the factorials.
Okay.
So I'm actually gonna show you that in a second, actually, how you can do it out. So, in this one, when we have the ratio test, so we're changing all the n's to n plus ones. So it's n plus 1 to the n plus 1 power over n plus 1 factorial. And then the bottom one, in essence, all they're doing is they're flipping it over and multiplying it. So it's n factorial over n to the nth power there. So is everybody good to that? Did everybody see what I did with that step there? And then I'll show you how they simplify it down. Because the next part's where the factorials and stuff comes into play. All right. So the next part, they've split up the n plus 1. So they have n plus 1 times n plus 1 to the nth power. So they basically took that n plus 1 right there, and they split it into the two parts. The same thing I did with those 3's in the last problem when I had 3 to the nth power times 3. That's what they did there with the n plus 1's.
So how did you get the n on the bottom one next to the factorial?
This one?
Yeah, how did that get there?
All right, so now factorials. So if you look at a factorial is basically like 5 factorials, 5 times 4 times 3 times 2 times 1. That's what 5 factorial is. So if I have n plus 1 factorial, I can take out that n plus 1. So if you think about it, n plus 1 factorial, if I imagined it was the 5 down, that n plus 1 is 5. So that's 5. And now that's 4 factorial, which is 4 times 3 times 2 times 1. So I can take out that n plus 1 and then just leave it as n because that's the next term in the list of factorials. Does that make sense? Because if you think about a factorial, like if it was n plus 1 factorial, it would be n plus 1 times n minus 1 times n minus 2 times n minus 3 all the way down to 0. Or down to 1, I mean. Right?
Yeah, but then why is the factorial sign still there?
Because that n factorial is everything after the n. So it's the n minus 1, it's the n minus 2, the n minus 3, all the way down to 1. All I'm doing is I'm taking that first term out, that n plus 1 that was multiplied. So here, let's try this. So I have, so n plus 1 factorial. Actually, let's make this a little bigger. All right. So if I look at that, that's the same thing as saying n plus 1 times n minus 1 times n minus 2, and all the way down, right? To 1, correct? That would be n factorial, right? Or n plus 1 factorial, I should say.
Yes.
Okay. So all we're doing is I'm going to keep that n plus 1. And this part here, this is n factorial. Because that is the same thing as saying n times n plus n minus 1, n minus 2, all the way down to 1. Does that make sense, sister?
Yeah.
So that's where that part down the bottom comes in. And the reason I want that is because I want to get rid of the factorial piece. Because if I have the factorial piece, it kind of makes it a lot harder for me to actually deal with it. So the n plus 1s are going to cancel out now. The n factorials are going to cancel out. And I'm going to be left with just n plus 1 to the nth over n to the nth, which is that right there. Now, this is something you're probably going to want to write down because this is something that comes up quite often in these. and it's not something that's read like you just look and go, oh yeah, that's E. It doesn't like it's not something that's just going to roll off the tongue. So 1 plus 1 over the n to the nth power, the limit of that goes to E. So if you get anything to that thing right there that comes up to that, it's going to E. And since I'm doing the ratio test and E is greater than 1, this is divergent.
You said 1 plus 1 over n to the end is all the limit is always E.
Yep, that limit goes to E. Yep. And that's one that this book seems to really like. So it seems to come up in quite a few problems. So the chances of you seeing something like that on the test probably would be pretty high just because of how they write their problems. All right. So on this one, this is one of those examples that you could actually use multiple ways to do it. So on this one, they actually say, well, you could actually do the test for divergence because n to the nth power over n to the factorial. The top is always going to be bigger than the bottom. So the limit of this is going to go to infinity anyway. And since it doesn't approach 0, it is divergent because of the test for divergence. But we're going to look at more situations like this when we're looking at the in section 7, where we're looking at what's the best test to use for every one of them. You can use multiple tests. Sometimes it's just not the easiest one to do it. And this is one of those situations where the test for divergence actually would have been faster when you're looking at that one. All right, last test. The root test. It's the exact same thing as the ratio test, except we're not doing a ratio. We're not doing a to the n, a sub n plus 1 over a to n. We're just doing the nth root of whatever the function is, whatever the series is. But the rules stay the same. If the limit's less than 1, convergent, greater than 1, divergent, and if it equals 1, it doesn't work. If it doesn't work for the ratio test, don't try the root test. It'll give you the exact same answer. So, and the last problem, we could have actually done either test. The root test would have worked as well, but the answer wouldn't have, we wouldn't have been able to get an answer out of it. It still would have given us the same, it would have given us the same information. It still would have been divergent in that situation. So, but if the root test doesn't work, if I get equals 1, don't try the ratio test. I'm still going to get equals 1. So we have to try some completely different test at that point. All right, let's look at one example of the root test, and then we'll do a couple problems. So here's a simple problem. Notice how it's raised to the nth power. Notice the whole thing is raised to the nth power. That's where you really want to use the root test because it's going to get rid of that because you're doing the nth root of it. So when I take the nth root of this, I get 2n plus 3 over 3n plus 2, which I can easily find the limit of that. That limit's going to go to 2/3. And 2/3 is less than 1. So therefore, this series is absolutely convergent, therefore convergent. All right. Does that make sense there? That was pretty straightforward. Okay, let's look at a couple of problems. Let's do. All right. Find out if this one is convergent or divergent. You can use either so in this one, we wouldn't really want to use the root test because the whole thing isn't to the nth power. If the whole thing was to the nth power, then we use the root test. So since this one's not the whole thing to the nth power, we want to use the ratio test on this one. So that's what your ratio test should look like. I would almost never write it as the division. Just always write it as the n+1 version of it, and then flip the original version over for your second one. It's really messy when you're writing it as the division part. And once you get down to this part, the goal is kind of to try to simplify this down as much as possible. So in this case, it's going to have to deal with the -2 on the top and the bottom to work at simplifying it out. So when you simplify that, you get this. So I put the n squared over the n+1 squared, and I'm left with just one -2. And that's from the -2 to the first power because the n's -2 to the nth powers cancel each other out. All right, so the absolute value, the 2 can come out. If I'm just looking at the limit of this, the 1 over 1 plus 1 over n squared, that goes to 1. So this whole limit goes to 2. Since it goes to 2, what does that mean?
It's divergent.
It is divergent. So that means that the original series is also divergent. All right, let's do that one. We'll do a couple more. All right, try that one. So that's what you should get when you do the ratio test. And your goal when you're doing the ratio test, when you're trying to simplify things down, is you want to try to cross off as much as possible, and you want to get things with the same exponent together. So like I've got n plus 1 to the 100th and n to the 100th, so I'm probably going to put those two together. I've got the n factorial and n plus 1 factorial, so somehow I want to get rid of that n factorial. And then I have 100 n plus 1, and I have 100 to the n, so somehow I want to get rid of that 100 to the n. So if we break it down, we're left with 100 on top from the 100 n plus 1. And we're left with n plus 1 on the bottom from the n plus 1 factorial. And then I have the n plus 1 over n to the 100th power. So now if I look at that as the limit of n goes to infinity, so this 100 over n plus 1, that's going to 0. And the 1 plus 1 over n, that's going to go to 1. So 0 times 1 is 0. So 0 is less than 1. So this one would be convergent. All right, last one. Use the root test on this one. When you're doing the root test, it's always the nth root. So this, we're not doing to the 5 nth root, we're doing it to the nth root. So that 5 is going to stay. So we have the limit and then goes to infinity of 2 to the 5th, n to the 5th, and n plus 1 to the 5th. The negative sign disappears because of the absolute value. And then, so I have 2 to the 5th, which is 32, so that can come out in front. And if I'm looking at the limit of 1 over that bottom is going to go to 1, so it's going to go to 1. So 32 times 1 is 32, and 32 is greater than 1, so it diverges. So those are the tests. So we have the tests that we have. We have the p-series and the geometric series tests that we can use. And if we can show that either one of those, we know that for the p-series, if it's greater than 1, it converges. And if it's less than 1, it diverges. Or if it's between 0 and 1, it diverges. The geometric series, if it's the roots between -1 and +1, it converges. Anything outside of that, it diverges. Then we looked at the test for divergence. We looked at the integral test. Then we did the comparison tests. We compared them to different functions. And then we have the alternating series test. And then we have the root test and the ratio tests. So those are all the different tests that we looked at to figure out convergence and divergence. Yeah.
This test would be inconclusive because it's just 1. Is that right?
Nope, this is 32 because it's 32
Oh,
times the 1.
32. Yeah. Okay.
Yeah. Yeah, if the 32 wasn't there, it would actually be inconclusive. So if it was just n over n plus 1, it would be inconclusive because it went to 1. But since that 2 is there and the 32 makes it goes to, it's higher. So it's divergent. So Thursday's class, we're going to go through sections 11-7. Basically, all that is going over looking at all the tests and figuring out which tests we're going to use and then showing if it's convergent or divergent. And then next week we'll do the power series from 11-8, and then we'll review for the test, and then the test is on the 13th. So the review test is already up, so if you want to play around with the review test, it's already there for the chapter 11. So, and the recording.